Hello students, welcome to the third lecture in this series of lectures on simulations. Today we are going to see, in continuation of the other two techniques, general techniques that we have seen for simulating continuous random variables, the third technique that relies on hazard rate functions. In order to understand hazard rate functions, we actually need to study some theory related to stochastic process, and in particular we need to study how the Poisson process is generated. So first, in today's session we will start with understanding the Poisson process, use the Poisson process to generate hazard rate function, use the Poisson process to generate a random variable having some hazard rate function. So let me bring up my slides on Poisson process first. Okay, I'm back with the notion of Poisson process. So let us try to understand what is a Poisson process. A Poisson process is popularly known as a counting process. In particular, Poisson process can be defined in three ways. In this particular session, we will see two definitions of Poisson process, of which definition one is this. A stochastic process. What is stochastic process? A stochastic process is nothing but a family of random variables, maybe an infinite family, countably infinite family of random variables, which is the case here, having certain dependence structure and an index set on random variables. So in this particular set, the index set nt, t greater than or equal to 0, is positive side of real line. Nt is nothing but the counting process, and each nt will follow a Poisson distribution, which will come as a byproduct of this definition. So let us first understand what this definition says. The stochastic process nt is said to be a Poisson process with rate lambda if it is stationary and independent. It has stationary and independent increments. Further, it satisfies the following properties, that is n0 is equal to 0 is equal to 1 in probability. That is, probability of n0 is equal to 0. That means the Poisson process starts at time point 0 and has a value 0. Second condition is, in any short span of time, that is h interval of time, probability of nh is equal to 0 is 1 minus lambda times h. Lambda is the rate at which something happens. So 1 minus lambda times h plus order of h. That means those quantities can be ignored. Order of h means if something is of order of h, that means that thing upon h, limit as h tending to 0, will become 0. Then the third condition is, probability of nh is equal to 1 is lambda times h. H should be sufficiently small such that this lambda times h is less than 1. Okay. And the fourth condition is, nh equal to j in probability is of order h. That means all these terms as h tend to 0 go to 0. If these conditions are satisfied, we will say a stochastic process is a Poisson process. In particular, when you study theory of stochastic process, you will derive that this Poisson process actually have marginal distributions which are Poisson distributed with parameter lambda t. Similarly, we have a second definition of a Poisson process, which is given in terms of the distribution of interarrival events. So here is a second definition. If xn is a sequence of non-negative random variables representing the time between two consecutive events, this time between two consecutive events is called interarrival time, and it is random. Right? That is why we are denoting it by xn. Now you define S0 to be equal to 0. What is S0? It is actually a constant random variable 0, and Sn is summation over I equal to 1 to n xi. So this Sn actually counts the index of Sn actually counts the number of events that happen in the interval summation over xi. All these time intervals are random. So in particular, I will define my NT, which is similar to the one in the definition one, as maximum over n greater than or equal to 0, such that Sn is less than or equal to t. What does this mean? This means in this random interval of time where n events have happened, that random interval of time is less than or equal to t, and the number of events that can happen is indexed by this set n, and if you take maximum over all n greater than or equal to 0, then you will get the number of events in time 0 to t. This NT in general is called a counting process generated by Xn. However, the special case of this is when Xn's are exponential with mean lambda, that is rate 1 by lambda. Sorry, exponential with mean 1 by lambda, that is, and rate lambda. So if Xn's are exponential, then NT, the underlying process which is defined in this manner, NT is equal to maximum over n greater than or equal to 0, or NT is defined like this. So this is the NT. So this definition of NT is valid, and then if xi's are exponential 1 by lambda, then I will get a Poisson process with rate parameter lambda. So in particular, this process can be simulated. As we already know how to simulate a random variable with exponential with mean 1 by lambda, we can easily simulate this process using the definition 2 of this particular process. That is, let us now see the algorithm. In algorithm, what you will do is you will fix the parameter t over so in the interval 0 to capital T over which you want to simulate a Poisson process. What happens is when you are considering xi's, the xi's are actually exponential with 1 by lambda. So whenever each xi, whatever you simulate, the value of xi, at that point in time, one event must have occurred. Correct? So in that case, NT, so the first simulation of x1 will give me n1. That is, nt is equal to 1. Whenever that, whatever is the value of that xn, n of that value is equal to 1. Okay. This way you will continue till you reach the capital T, which is fixed. Okay. So if I want to simulate this particular process, then how will I do this? I will first start with n is equal to 0 and t is equal to 0. This is taking care of the condition that at initial point n of 0 is equal to 0. Now you know you have to simulate the interarrival distribution. So what is the interarrival distribution in case of Poisson? As it is mentioned here, it is xn with mean, xn follows exponential with mean 1 by lambda. So I will simulate a random variable y with mean 1 by lambda. Now first, before simulating that random variable, you have to check whether t is less than capital T. As we are starting initially, so t will be less than capital T. The small t will be less than capital T. Therefore, I will generate y following exponential 1 by lambda. If somehow it happens that the small t is greater than or equal to capital T, then I will stop the algorithm. Otherwise, I will continue. So in the first iteration, let us say n is equal to 0, t is equal to 0. 0 is less than capital T. Therefore, I have generated one exponential random variable with mean 1 by lambda. Once generated, this is, remember, this is nothing but a random time at which the first event has occurred. So then what I will do is I will add that random time to my time. Therefore, I will set t is equal to t plus y, and I have to count the event. So n is equal to n plus 1, right? So that is the time at which the first event has happened. That essentially means in this particular case, I am saying something like n of y is equal to 1. In this particular case, when t is equal, when I start with t is equal to 0, n of y is equal to 1. Then again you will go to step 2. You will check whether this new value of t is less than t or not. If it is less than t, you will generate an exponential random variable and go to step 3. If it is greater than t, you will stop the algorithm. This is how you will generate a Poisson process with rate parameter lambda. Now we want to use this knowledge to understand our hazard rate function method. But before going to hazard rate function method, let us recollect that if I have an exponential random variable with rate parameter lambda or mean 1 by lambda, then exponential distributions are very special distributions having memoryless property. That is the property derived here. If I consider the conditional distribution of x greater than t plus s upon given that x is greater than s, and if I consider this probability will always be equal to probability of x greater than t. This is called memoryless property. In some of the offline classes, we have already shown that if it has a memoryless property, then it must be exponential, and if it is exponential, then it must have a memoryless property. So we can easily prove this property using this particular calculation. Let me go through quickly. So if x is greater than t plus s, given that x is greater than s, then you can easily see that x greater than t plus s is a subset of x greater than s. Therefore, if I use this conditional distribution and if I take the intersection of these two events, this event and this event, then it turns out that this event is a subset. So I will have probability of x greater than s t plus s as a numerator and probability of x greater than s as a denominator. Since I am dealing with exponential random variable x, I will have the distribution, the 1 minus the CDF of that is e raised to minus lambda times t plus s, and the denominator as e raised to minus s lambda, which will give me e raised to minus lambda t, which is equal to probability of x greater than t. For all t greater than or equal to 0, this condition is valid. Therefore, the distribution exponential has memoryless property. Now we have proved that exponential distribution has memoryless property. We have also seen that exponential distribution can be used to generate a Poisson process, and now it's time to go to hazard rate function method. So in order to consider hazard rate function, we will see what is the definition of hazard rate function itself. So if I have a random variable t which follows f, which is a continuous distribution, this is a CDF of the continuous distribution with f0 is equal to 0, essentially that means it's a non-negative random variable. Then lambda t is defined to be hazard rate function of this CDF f, and is given by lambda t is equal to f dash of t upon 1 minus f of t. Because this is a continuous distribution, that f dash of t is nothing but a density, and our goal is to consider this random variable having hazard rate function lambda t. So let us go to our goal. What is our goal here? I want to simulate a random variable s with hazard rate function lambda t. How will I simulate this random variable? As you can see, this hazard rate function had some commonality with exponential distribution. As a quick look, if you consider exponential distribution as a distribution of this, if t follows exponential random variable, then you know exponential random variable with mean 1 by lambda, then you know ft is lambda e raised to minus lambda t upon 1 minus ft will be e raised to minus lambda t. So you will get this lambda t is equal to lambda as a hazard rate function. Now I want to use this knowledge to my advantage, and I want to simulate a random variable s having hazard rate function lambda t. So the basic idea is, just now I have seen how to simulate a Poisson process. So can I use my knowledge of a Poisson process and simulate this particular random variable? Let us try to figure out. So let me give you a brief idea of possible algorithm. Suppose I choose some lambda such that this hazard rate function is bounded above by this lambda t less than or equal to lambda, for all t greater than or equal to 0. If I can do this, then I know how to simulate a Poisson process with rate lambda. And if you recollect the algorithm of a Poisson process with rate lambda, you are simulating one event at a time. So now, if some event happens, at time t, I want the hazard rate function to respect the function lambda t. Right? So if some event happens at lambda t, what I will do is I will try to accept that event with probability lambda t by lambda. Is that justified? Yes, because if you look at lambda t is always less than or equal to lambda. So lambda t by lambda is always going to be less than 1. This is as good as simulating some uniform random variable. Though this is not a uniform random variable, but the analogy is similar. So this is my idea. Now I want to figure out, if I use this algorithm, whether I will be able to generate a random variable s with hazard rate lambda t. In order to understand this, let us try to put this as a theorem in the next slide. That is, the time of the first counted event. So we are actually counting the time, not the event. The time of the first counted event, say s, has hazard rate function lambda t, where t is greater than or equal to 0. This is what I want. So how we will count the time? Using the algorithm idea that is given here. So what I am doing, step 2 is important. For step 1, essentially I am saying I will choose a lambda that always bounds lambda t for all t. Step 2, I will simulate a Poisson process, and step 3, I will actually accept the counted event of a Poisson process with probability lambda t by lambda. So this is actually giving you some kind of proportion. Lambda t by lambda is the proportion of acceptance. So let us try to understand what this will do. So what I will first do is I will consider a small interval of length dt, and I will see if s is greater than t, what happens in this interval t to t plus dt. So what should be my conclusion? That in this interval, if you look at our definition of hazard rate function, in this interval, I should get the entire computation in terms of lambda t, which is ft upon 1 minus ft. So I should be able to show that if I use this method, and if I consider this particular computation, then I should be able to show that this had some relation with lambda t, or this is exactly lambda t plus some error term at most. Okay? So this is what my goal is. So now you look at this event, t less than s less than t plus delta t, given s is greater than t. I can write this event using algorithm that this is the first counted event in the interval t to t plus delta t, and there is no counted event prior to t, because the time of the first counted event, right? So there is no event which is counted prior to t. Okay. So in this particular case, how I am generating? I am generating it using a Poisson process. So that essentially means if at all the event happens, it should happen with a by respecting the Poisson process. Correct? Now, if it has to be counted, that means there are two conditions that should be valid. That is, it may happen that a Poisson event may happen, but it may not be counted. Then it will not come in S. So it's an intersection of two sets. That is, a Poisson event happens in the interval t to t plus delta t, and it is counted as well. Okay, and there are no events prior to t. Now we will use the memoryless property that we have discussed for exponential random variables, because the interarrival times are exponentially distributed. Therefore, if the Poisson event happens in t plus delta t and it is counted, given that no events prior to t are counted, the no events prior to t are counted due to memoryless process is invalid. That means what I will worry about is the Poisson event happens in the interval dt. The t doesn't have any significance. Poisson event happens in the interval dt. Or you can simply replace this by 0 to 0 dt, and it is counted. So it means that a Poisson event has happened in the interval. So this is actually a mistake. Let me annotate it. This Poisson event, 1 minute, I will do it. This thing should be 0. This thing should not be there. Essentially, it should be from 0 to dt. Okay, so Poisson event happens in the interval of length dt, and it is counted. So what is if you recollect the first definition of Poisson process, the probability of this is actually lambda times dt. So the probability of this is actually nothing but lambda times dt plus odt. Remember that lambda h plus OH. So the Poisson event happens is lambda times dt plus ODT, and independently we are choosing whether it is counted or not with probability lambda t by lambda. Yeah. So now if you do appropriate calculations, what does this mean? This means it is lambda, the probability that in this interval t to t plus dt, S will take a value is lambda t dt plus odt. Now, if I want to consider lambda t, then I have to take limit as dt tending to 0. That essentially means the hazard rate function of this S is nothing but lambda t, because the term containing odt will go to 0 as I take dt tending to 0. Okay. Therefore, I have proved that the random variable generated by this process, this algorithm, is actually giving me a random variable with hazard rate function lambda t. Now, this is important for studying lifetime distributions. So in particular, what is our algorithm? Now let us make the precise algorithm. Choose lambda such that lambda t is less than or equal to lambda for all t greater than or equal to 0. This is the first step. After that, the second step in the idea was to simulate a Poisson process. Now we can give some more general steps like generate pairs ui and xi such that xi follow exponential lambda 1 by lambda. This is what we have been doing for simulating a Poisson process with lambda. Right now, this ui is a new addition. Right, so if this ui follows uniform distribution, then you can stop at n, which is minimum over n, such that un is less than or equal to lambda t by lambda. Lambda t is given by this. Okay. So here they are not fixing a capital T, but they are allowing some n iterations to happen so that this un is less than or equal to lambda t by lambda. Okay. In this particular case, we will go further. Now this n is there, right? And I know this xi. I don't want to simulate a Poisson process here, but I want to simulate the time distribution. That means I want to simulate the time of the first counted event s. So what should be my s? I should take this n, and I should only consider the random variables xi up to this value n, capital N. Right? So I will set s is equal to summation over I equal to 1 to capital N xi.